In this example, we're going to take a look at how to show a subset as a subspace. We have to show then that it satisfies all three of our conditions. The first being that it has the zero vector, which guarantees that the set is not empty. We have to have closure under vector addition, and we also have to have closure under scalar multiplication. So let's go after the first part of this, which is showing that it contains the zero vector. And this is really pretty easy. We can do it by taking x1 equal to 0, since it's free. And if we run that into our conditions, that shows that x2 is equal to 0 and x3 is equal to 0. So clearly the zero vector is in the set. Now let's go on to the second condition, which is that we have to have closure under vector addition. And we have to do this by taking a couple of generic vectors. So I'll take a vector u and a vector v. And we have to choose these generalized vectors. Otherwise, all we do is show that it works for a specific pair. But we really need to show that it works for every vector in the set W. So here's our two vectors, u and v. And we'll go ahead and make sure that those are in W by imposing the conditions that are supplied in the initial statement here, which is that x2 is 4 times x1 and x3 is 5 times x1. So that means that u would take the form u1, 4 times u1, and 5 times u1 in order for it to be in W. And v would take the form v1, 4 times v1, and 5 times v1 for it to be in W. Now we can add those two things together. So vector u plus vector v, and we just use our normal concept of vector addition here, adding the corresponding elements, would be u1 plus v1, 4 times u1 plus 4 times v1, and 5 times u1 plus 5 times v1. So there's what we get when we add those two vectors together. And then what we have to be able to do is show that this new vector is also in W. And we do that by factoring out the coefficients on the second and third elements there. First one is the same. Second one looks like 4 times u1 plus v1. And the third element is 5 times u1 plus v1. And it's pretty tempting to want to just jump right to the end of this. I really want you guys to write out these intermediate steps in here and not just immediately jump to it the end here and say, oh, it's closed. I really want to see all the steps. I know it's a little tedious and it seems a little trivial, but it's one of those important details I kind of want to make sure that we get. Now we are at the end of this, and it turns out that this does satisfy the condition of being in W. So we can say we have closure, so that's good. So closure of our vector addition. So that condition is met. So we can check that off. And we also had the zero vector, so we can check that off. And the reason why we can say that this is in W is you'll notice that here's the first element, the second element is 4 times the first one, and the third element is 5 times the first one. So it satisfies the appropriate conditions to be in W. So we have that closure. So now let's look at the last condition, which is closure of scalar multiplication. So let's again take our generalized vector u. We can't again just show it for one specific vector and one scalar. That doesn't work. So we take u here, and it's going to be in W. Again, it has to satisfy those conditions. So to be in W, it would take on the form u1, 4 u1, and 5 u1. Again, just applying those conditions. And then we can multiply it times a generalized scalar a. So then a times the vector u is going to be equal to AU1, A times 4U1, and A times 5U1. And again, I know this seems a little tedious to have to write this out, but I think it's important enough that we need to be careful about how we're writing out these steps. So this is AU1 and then 4 times AU1 and 5 times AU1, just flipping around the order there. And now, again, we see that this is in W. And we know that, again, by the appropriate conditions. I've got the first element, the second element is 4 times the first element, and the third element is 5 times the first element. So we verified that, in fact, this is closed under scalar multiplication. So our three conditions are met. So this subset that we've specified up here at the beginning W, this particular subset here is in fact a subspace.